So yeah, hi everyone. My name is Romeo Radanyi. I'm a director from the newly created Moody's quantum computing function. My main role is pretty much focused on how can we connect the dots between the classical capabilities that we already deploy and host in public cloud, but also the potential of quantum computing, and also supporting our researchers in quantum to make the best use out of some of the quantum capabilities. And here I am on stage with Gustavo, who is a senior director from the predictive analytics function, focused on how to solve some of the integrated risk assessment challenges that we have. Right, so in case if you haven't heard of Moody's, and what do we do? So Moody is a global integrated risk assessment firm. We provide financial information, financial data, financial intelligence, and analytical solutions and insights to our customers to enable them to make better decisions faster. And ideally, as quantum computing advances, hopefully at least quadratically faster. But what does that mean? Like, are we a data company? Are we an analytics company? Are we a credit opinions or credit rating company? So Moody's Corporation was actually founded in 1909 by John Moody, so it's more than a 100 years old company. And based on that wealth of experience and century of experience, which started off actually providing manuals of statistics of stocks and bonds and bond ratings to customers, the company was built. The credit rating opinion business is called investor services, and as you can imagine, very heavily regulated. Moody's Analytics, on the other hand, emerged in 1909, outside, basically from being a business unit, and initially provided quantitative analysis services to customers and capabilities around risk assessment. It grew through acquisitions and partnerships to the point where today we pretty much provide information about risks of someone's portfolio, supply chain, commercial real estate, cybersecurity, potentially know your customer or the KYC space even, or your ESG score. But also most recently, we even got some acquisitions of RMS, who has some of the most prestigious data sets in the climate space. So we can even look at information around the risks of climate impact itself on any of those that I just mentioned. But our customers need an integrated perspective of all those risks. So that's exactly what we're focusing on now. And with that, I hand over to Gustavo, who is going to talk about how we're tackling some of the integrated risk challenges.
Thanks, Romeo. OK, so I'm going to be talking about integrated risk analytics and how we are thinking of connecting this with quantum computing. Right, so as Romeo was saying, Moody's Analytics in particular is in the business of providing data, insights, and solutions to our clients so that they can make better decisions faster. That is what we are all about. And in that process, we have opinions, we have data, we have tools to assess many different types of risks. And we develop best-in-class insights on these risk types, but they are very much siloed assessments. What me and my team have been tasked with doing is combine these risks in a coherent basis so that people can really understand how much exposure they have to these different risks on a like-for-like basis and make decisions on which risks they are more important to and which risks they should focus on, depending on the type of assets that they are interested in, and also very importantly, the time horizon they are thinking of. So in the rest of the presentation that I'm going to cover, what I'm going to tell you about is a little bit of how we're actually building these solutions, and also how we think that quantum computing could actually enhance these particular applications. And this is basically the philosophy behind how we're actually thinking about utilizing quantum computing at Moody's. Is in this way, is embedding the power of quantum within the solutions that we already deliver and offer to our clients, so that we can increase accuracy, we can increase speed, and we basically give better solutions, better offerings to our clients. Okay, so it might sound simple to just take different risk types and combine them into one single metric, but it's actually not simple at all. It's a very complex problem with many parts. And I'm not going to go into full details because obviously we don't have time, but just to give you a glimpse on how we're developing this. What we do, we borrow from techniques that are commonly used in financial risk management, in particular scenario analysis, stress testing. So we start with scenarios. These scenarios are multi-year views on what can happen to the economy. They mix views on expectations around inflation, expectations about employment, but we also mix it with expectations about what's going to happen to climate risk, for example. So it's a combination of macro and climate risk. And we call these our sources of systemic risk because they cover basically, well, they cover the globe, but they affect many countries or entire countries at once. So these type of resources are common to all the assets in one of our clients' portfolio, for example. So we start with that, and this is a finite set. It's a relatively small set, around 15, 20 of these anchored scenarios. And what we do is to expand them stochastically. So we generate entire distributions of this type of scenarios across time. And we do this for two main reasons. One is that it allows us to minimize the bias of selecting these 15, 20 possible scenarios what's going to happen to the economy and the climate. So we cover many, many more. But also allows us to use statistical techniques, based on probability theory, to do this integrated risk metrics. What we do after the stochastic expansion is to overlay what we call idiosyncratic shocks. These are things like, just to make the distinguish between what we say is systemic versus idiosyncratic. Systemic is these macroeconomic climate scenarios, whereas these idiosyncratic shocks can be specific weather events like a hurricane hitting the Florida, for example, right? So that is more constrained in location. It would be a smaller set of assets, or it could actually be specific, like a cyber attack that affects a particular firm only. So it's a firm-specific type of peril. So we overlay for each of the stochastically expanded scenarios that could actually affect all the assets in our client's portfolio. Then we overlay this type of shocks at points in time, and that will shift the distribution of what impact this risk could actually have on the assets. And notice that I have been talking about assets in general, and that's because we're developing this framework such that is asset agnostic. So we can cover firms as a whole. We can cover financial assets like bonds or loans that are linked to particular firms, or actual real assets like commercial real estate or houses. And the idea and what glues everything together at the end is that we translate these different resources, both systemic and idiosyncratic, into impacts on the value of the asset. So at the end of this process, what we have is a distribution of asset values for each asset in our portfolio. And one of the innovations that we bring in is that we can then use analytical solutions that allows us to actually do this risk integration really efficiently. We would actually need, this is the only part, the integration is where we actually don't need a quantum computer. But in each of the other steps, as I'm going to mention later, quantum computing algorithms could actually be, could improve the efficiency and accuracy of what we're doing. Okay, so, all right, so now, so what? So we have these. What is it useful for? Right, so one thing that you can do once you have these integrated risk metrics is do risk-reward type of analysis. You can look at the y-axis in these plots is the volatility, and the bottom is, or the x-axis is expectation. So this looks at the asset return expectation over volatility for a particular portfolio. So you can then understand how different assets would be impacted. So what are the riskier ones? What are the ones that are going to give you the lowest return with the highest volatility when you take into account all the different risks that we capture in our integrated risk framework. And obviously, you can also do it risk by risk. So you can also select, OK, what I'm interested in is on climate risk or ESG risk or cyber risk. You can do this type of analysis on a risk basis. But you can also do it taking into account all the risks at once. And you can do these, obviously, select different countries, different industries, and also different time horizons. And this distribution will actually change depending on the time horizon, because different risks will be more material depending on the time horizon. And then, because you do this at the asset level, then you can obviously aggregate it up and understand how different risks are concentrated on different parts of the portfolio across countries and industries. And you can do country-to-country comparison across industries. Like in this plot, we're comparing Germany versus Singapore, and we're comparing all different type of risks. And here you can actually say what are the risks that are more material for this particular portfolio on a 15-year time horizon. So you can take actionable decisions on which risks you should insure, which risks you should offload of your portfolio if you can, or which risks you can hedge if that's an option for your organization. OK, so now very quickly, so going back to the different stages of the process, there are already published research that could be utilized in the future, not now. They are typically algorithms that require a fair amount of fault tolerance. But if we want to be able to capture this in the future, we need to take into account how we're going to build it. And this is something that Romeo is going to cover in the remaining of the presentation. But things like better way of forecasting the macroeconomy. That would be one of the areas that could help this particular framework. Also, generative models for better, more accurate expansion, stochastic expansion, that learns the features of what actually really drives the noise in macroeconomic and climate forecasting. Better ways of doing weather forecasts. And obviously, another thing that we could leverage is quantum machine learning, where we have a limitation how many assets we can actually run this framework through on a relatively timely fashion, say around 1 million assets on a 1-hour batch. But if we wanted to cover millions and millions of assets, in our firm database, we have 400+ million of companies. So if we wanted to expand that, what we're developing is machine learning model that basically learns the features from the output of the model and then predicts what the output of the model would actually be for firms that we have not actually run our model through. And that is another area where quantum machine learning could actually bring benefits in the future. And with this, I'm going to pass on back to Romeo.
Thank you. So yeah, why do we act now? I guess from you could hear from Gustavo, there is a lot of overlap in terms of like the power of quantum computing and solving complex problems, and obviously Moody's wants to capitalize on those capabilities. We also position very uniquely in the financial industry in a sense that we have some of the best data sets and award-winning products in terms of risk analytics and also some of the best quant delivering models to our customers as well. For example, we have the famous Orbis dataset, which has more than 445 million public and private entities. Or in terms of commercial real estate, we have datasets about pretty much all the commercial real estate in Manhattan. And we do believe that if we harvest the potential of quantum computing when the time arrives, we are very well positioned to achieve business advantage through that. But how do we march towards that vision? Well, that's exactly why we created the quantum computing organization or function within Moody's as well. And we have some very specific focus areas. I mean, one of them is very, very much obvious, focusing on security and defense. I mean, as you can imagine, especially credit rating opinions are quite confidential information and something we need to protect, and also our communication channels. So we need to invest into protecting against or the threat of quantum computing as well. And not just for our own data sets, but for our customers as well. The second area is what Gustavo was touching on as well, is identifying the various products and use cases where we believe quantum computing could potentially provide either speed up or some benefits in terms of accuracy or just providing faster calculations. We're also keen to collaborate with our customers and clients as well. So if you're interested in use case exploration, feel free to reach out. We would love to talk to you. And then third, in the classical domain, we are very well positioned and our quants delivering models on a daily basis. So we want to obviously provide training and material for our quants as well to get quantum ready. But we also, while we're creating the data set and training, we will make that available through our learning platforms as well for our customers if someone is interested in getting started with quantum computing. And then lastly, we are very, very aware how important the community engagement is, especially academia and research organizations, because who knows whether the next algorithm will come out of some of the research that one of the universities are doing. So we very, very much want to get engaged in those domains as well, potentially sponsor PhDs or certain academic research opportunities as well. As you could tell by now, we're not here to provide you like a brand new research paper we just released, especially because the group is fairly new, but rather we approach it in a different way. We have a different strategy. We're trying to look at some of the practical side of potentially applying quantum computing to some of our existing products even, and infuse maybe even access to some of the quantum capabilities with our unique data sets and our classical products. We believe that product integration is going to be key, and also understanding the end-to-end pipeline between a classical capability and a quantum capability as well, because even reading out or getting data in and out is very challenging, and not to mention benchmarking or even finding those crucial indicators that would provide you information about whether you even are gaining anything out of quantum. And I guess what I do want to say here as well, that ultimately we do not care when quantum advantage really happens. We do want to be prepared for it, obviously, and throughout that learning journey, we want to build up enough experience as well that when it arrives, we already have classical products that's either hooked into some of the quantum capabilities or platforms that can then benefit our researchers and also our customers as well to utilize our data for their own quantum development as well, especially because we serve pretty much all the banks, tier 1, tier 2 banks, and we want to make sure that those clients who maybe doesn't even have a quantum team can use our platforms potentially to do research. And then on the last slide, what I want to say is that our observation in terms of the quantum market, and I'm sure others probably share the same sort of sentiment as well, is that it's a challenging one, right? Like there's a lot of different vendors, a lot of different claims, a lot of different hardware providers, a lot of different software providers. It's very difficult to actually get a good assessment in terms of what is exactly going on, which one is closer to some benefit or not. And also, the financial companies are all looking at the exact same problems to some degree, right? Like we've probably heard portfolio optimization 15 times today, derivative pricing, or all the other use cases that everyone is looking at to solve, or even Monte Carlo simulations itself. But there could be a benefit in some other areas as well, or maybe even creating products around quantum computing that we do not even know of. So that's why we are very interested in collaborating in terms of use case exploration. But also, if you are interested in creating a community of industry-leading and innovation experts in the quantum computing space, focused on financial use cases, please talk to us as well, because we're all researching the same thing, we're all looking at the same set of problems, and right now there is not really truly any competitive advantage anyway, so we might as well collaborate in some of those areas. And with that, I conclude the session. And thanks for listening.
Thank you. Any questions?
I just had a quick question. Obviously, efficiency is always mentioned in every presentation. You also touched upon accuracy in one of your slides. Which specific use cases did you see with the current quantum computers available where you've had higher accuracy using quantum compared to classical? And where do you anticipate the higher accuracy as well in the future with better computers?
Yeah, I mean, typically, accuracy is linked to either runtime, if it's simulation-based, or better models. So basically on those two areas. So if we can get faster simulation, for example, then we will get better accuracy, less Monte Carlo noise. But also we can actually get better models, like in, as Raf was talking about predicting downgrades. That's something that we very much do as a matter of course, at Moody's. So we can actually increase the accuracy as Crédit Agricole has demonstrated, then is something that we are very much wanting to explore and understand how.
Any other questions?
So you mentioned many different data sets that you have access to. So I wonder if you have a strategy of integrating like big data and quantum computing. So far we are able to incorporate in small data sets and quantum circuits. Do you have any idea how you utilize all of those data sets?
Yeah, I mean, we're definitely using big data now for our data solutions. I think that integration between quantum and big data is very far into the future, because actually loading classical data into a quantum device is one of the pieces that is more complex, and one of the things that the industry needs to actually solve, make it more efficient. So we don't have a strategy there, but I don't think that we should have a rush into actually, we need to better understand first how the industry can tackle that issue before we can start worrying about. But given that, I'm going to let Romeo ask, because thinking ahead probably makes sense in terms of. But I'll let you answer that.
Yeah, no, I mean, I think in this particular case, I mean, to your point, right, like we probably need to focus on constraint problems first, right? And then later on, as we can even solve some of the constraint problems, then I think the challenge on the integration between the classical domain, how you store data, how that gets in and out, is definitely going to be a lot more crucial. But we're probably going to have to rely on some of the cloud providers where most of our classical capabilities already run and exist, right? And our data gravitate compute, right? So there will be a lot of dependency on how these quantum hardware providers will be also probably going to have more than one hardware in one region as well, and then how those latencies will have implication on many of these things too. But yeah, I think we are further away from the big data challenge for quantum specifically just yet. But
one thing I would add is that one thing that we want to make sure is that the pipelines for our analysts, our quants, we want to make it as easy as possible to utilize quantum in the future. So right now, our data science pipelines will be connected to big data environments. So we want to ensure that we keep the same easy access to the data that they use to train their models once quantum tools are available, right? So we need to make sure that we integrate quantum capabilities within the existing data science pipelines.